Welcome to the discussion of random variables part 2. So let's pick up where we left off on the last last podcast. So we talked a little bit about what a discrete random variable was and what a continuous random variable was. Now, one of the main things we needed to remember was that if you're a discrete random variable, then you can count the number of items that show up in the list for the random variables. In other words, my x's are a countable number of distinct values. Now, it can be infinite. The reality is the ones we're going to look at this semester are going to be finite. In other words, you're going to be able to write down everything that's going to be in the list. You won't have to do it forever and ever. Okay, if it's a continuous random variable, then it can assume any value in a collection of intervals. Now, just to keep you kind of abreast of what we're doing here, the continuous random variables that we were looking at, or continuous models we looked at in the previous section, were both the normal and the uniform distribution. So we've done a little bit of talking already, actually, about continuous random variables. So the focus in this particular chapter is going to be on the discrete ones. That said, we do want to contrast how do we graph a discrete probability distribution versus a continuous one. Well, notice when we talked about the uniform and the continuous ones, we drew a smoothed curve or a line segment, and those density curves corresponded to our probability distribution that was continuous. Well, in the case when we have a discrete probability distribution, what we're going to draw is typically what are called a mass function or a stick graph. And in the mass function or a stick graph, what you've got is across the x-axis, you've got the values that the random variable can take on, excuse me, and then the height will be their corresponding probabilities, okay? So notice that you don't have to fill in the bars or anything like that. You just draw a stick. Say the values are 0, 1, 2, 3, and 4 that the random variable can take on, and then the corresponding heights that you have here, the heights of these bars, okay? The heights of these bars represent the probabilities, all right? Okay. A couple of things to keep in mind about a probability distribution of a discrete random variable. The distribution of a discrete random variable x is a table rule that assigns a probability to each of the possible values of the discrete random variable. And straight from the textbook, we talked about it actually in the previous section of this podcast, is that we know probabilities have to reside between 0 and 1. They've got to be greater than 0 and less than or equal to 1. Be careful about that. You're going to get output from your calculator that'll look something like this. There's an example, say 2.36 blah 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 e negative 7, okay? Now, many folks, the blah 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 part, they don't bring their eyes over far enough to see the e negative 7. You got to realize that what this number is this is 2.36 times 10 to the negative 7th, which means there are 6 zeros in front of that 2, okay? So make sure you realize that that's not 2.36 as the probability, okay? Keep that in mind. We'll talk about it more as we come across it. Okay, and then when I add up all those probabilities that show up in my probability distribution, the sum of those probabilities have to total to 1 in order to be a proper probability distribution. Okay, so let's take a look at an example. This is example 712 from the textbook. X represents the number of people in an apartment, and assume the maximum in a single apartment in this studio apartment is 7 people. That's people sleeping everywhere, in the shower, every place, okay? What must be the probability of 7 people in a household for this to be a legitimate discrete distribution? Well, for it to be a legitimate discrete distribution, all of these values here added together, including the missing value, have to sum up to 1, right? So we've got 0.2 plus 0.32, which gives us 0.52, right? So 0.52 plus 0.18 gets us 0.7, right? Because that's, 0.52, yeah, that works, 0.7, and then that gives us 0.85, and then 0.85 plus what? 0.07 gets us 0.92. So we got 0.92 plus 0.03 gets us 0.95, so 0.95, so we got 95% everything up to 6, so what must be left is 0.05, because the whole thing's got to add up to 1, okay? Let me make my 0.05 a little nicer there. That was a little ugly, so let's try that again here. Let's see if I can do a little better. Yes, much nicer. My daughters will be happy with me. Okay, so they ask us to display this probability distribution graphically. Now, we just talked about the different ways of graphing one of these distributions. Probably the best way to do it would be a stick graph. I'll show you a stick graph here. Here's a stick graph where we take each of the values that the probability distribution was assigned. Those are 1 through 7, this number of people living in the apartment, and then draw the sticks up to the heights being their corresponding probabilities. Of course, we've turned those into decimals if they were fractions. If they happened to be given to us as fractions, we would make those decimals. Okay. Now, another way you can do it is what's referred to as a probability histogram, and these are very commonly used in the real world because you can get a computer to draw them very quickly for you, or even your calculator. So these two graphs are synonymous and can be interchanged. You can do either one. You can either do a probability histogram where the width of the bars will always be equal to 1, and the heights again will be their corresponding probabilities. And one of the nice things about a probability histogram is that the area in each of these rectangles is exactly the same as the probability. In other words, that the height and the area correspond to each other. That's why? Well, because the bases are 1 and everyone, and the heights correspond to their probability, so length times width gets you the probability. So the area in here, for example, would be 0.2. Okay. All right. So let's go back here. I got myself a blank sheet of paper to do some work here. So what is the probability that a random chosen household contains more than 5 people? All right. So let's write down what that notation means. We want a randomly chosen household contains more than 5 people. So x is more than 5 is what we're looking for, right? Let's take a look. See, more than 5 is x greater than 5, right? So more than 5 would be what? It would be the probability of 6 or 7 occurring. So probability of x being greater than 5 is equal to the probability of x being greater than or equal to 6, which is equal to the probability of 6 plus the probability of 7. Okay? Hopefully that's making a lot of sense to you there. Let's go back and get those numbers from the table. So that looks like it's about 8% of the time, or 0.08, that that's going to happen. Because this was 0.03, that was 0.05, add them together and you get 0.08. Okay? All right, let's go take a look at the next question. What is the probability that a randomly chosen household contains no more than 2 people? So what do we mean by no more than 2 people? So that would be 2 or less, right? No more than 2 means you can have 2, but you have to have 2 or less. So in that case, in that case, we want the probability of x being less than or equal to 2. Well, the probability of x being less than or equal to 2 is the probability of 1 plus the probability of 2. So, looks to me that's about what? 52% of the time, right? So you got what, the 20% plus the 32%, which gets you 52%, or 0.52. So about 0.52 for that probability. Now let's stop for just a second. I want to point something out really important to you here. Is I want you to notice something, is that this inequality symbol makes a big difference in the outcome based upon whether or not it's a less than or equal to, a less than, a greater than or equal to, or a greater than. The endpoints are very important in discrete distribution, whether the endpoint is included or not. Now it turns out, and we'll discuss this more when we get back to continuous distributions, is in continuous distributions it doesn't matter whether we include the endpoint or not. Real big deal though when you're talking about discrete. Okay? Alright, let's go back and answer our last question here. It says, what is the probability that a randomly selected household has more than 2, but at most 4? Okay? So more than 2 means you can't have 2, right? At most 4 means you can have 4, alright? So what would that end up looking like? That would be the probability of 2 being less than x, but less than or equal to 4, right? Let's make sure you got that, okay? It's strictly more than 2, but at most 4. So that's going to be what? This is the same as the probability of your random variable going between 3 and 4, right? Which is simply the probability of 3 plus the probability of 4. Okay, so probability of 3, right direction here. Probability of 3 and 4, let's see, that's 0.18 plus 0.15, which is going to give you what, 0.33, right? Okay, because I'm going to see 0.33. So that's equal to 33%, or 0.33. Okay. All right, well, that's a good introduction to random variables. Hopefully you kind of got the hang of it. We're going to talk soon about how to create one of these ourselves. I'll see you all back here soon.